Hello. So my apologies for the delay. We had some technical problems. I am delighted to be kicking off the NYU Abu Dhabi Institute lecture series for the spring with a talk by Professor Stephon Alexander, Professor of Physics at Brown University. Please stay tuned for the upcoming public talks that will be focusing on politics, physics, and scientific research, among others. We are also hoping to have a live session during Ramadan. We will keep you posted. I want to take this opportunity to thank Nahed Ahmad, Assistant Director of Public Programming at the Institute, for organizing and managing the Institute's public lecture series. I am delighted Provost Peters is with us this evening. He will be introducing our speaker for tonight. For those of you who don't know, Provost Peters, he joined NYUAD as provost in September 2020. Prior to that, he was a Benjamin Powell Distinguished Professor of Mathematics at Duke University. And he was former Dean of Academic Affairs for Trinity College of Arts and Sciences, and also Associate Vice Provost for Undergraduate Education at Duke. Arlie Peters' principal research interests include mathematical physics and scientific methods in business administration, with a focus on mathematical finance and entrepreneurship and innovation in the STEM fields in developing nations. Provost Arlie, the virtual floor is yours.
Well, thank you, Nadia. And I know you have been here for just over a month, so I extend to you the warmest of welcome. I tell you today, it's quite a delight to be part of the first in our series, and even more delighted and have such a great privilege for introducing Professor Stephon Alexander, who is a leading scholar in the field of theoretical physics, a brilliant thinker, and a dear friend of mine. His talk tonight will introduce his latest book titled Fear of a Black Universe. He will take us through an extraordinary journey through some of the physics' greatest mysteries and lead us on an exploration of principles that shape all theories of the universe. And he's also going to combine music and cosmology that we call a cosmic jazz. But if I know Stephon, I can wager his talk and his book that there will be quite a lot of thoughtful, provocative ideas for you in the audience to think about. I also would like to say Stephon is not afraid to take risks, and he does not cower from the opportunity to make bold statements. From the opening chapter of his book, without giving any spoilers away, he says the time has come, and I quote, for a new Newton to reunite the physics of the extraterrestrial with the physics of the terrestrial. Thought-provoking and brave, Fear of a Black Universe provides a unique insight into the world of physics and asks earnest questions that inspire us. Professor Alexander's ethos of learning, penchant for exploration, and drive for curiosity are all pillars we believe in at NYU Abu Dhabi. And we are so proud to host him tonight. But beyond that, Stephon has been a stalwart force in the world of academia in calling on scholars to dispel structures that have limited racial diversity in our field. As a Black physicist, Stephon makes a powerful case for diversifying our scientific communities. A professor of physics, Brown University, Stephon is also the president of the National Society of Black Physicists and executive director of Harlem Gallery of Science. He's deeply passionate about education, promoting opportunities in STEM, and championing access to academic excellence. His latest book is yet another thrilling encounter with a scholar whose previous work, which was titled The Jazz of Physics, The Secret Link Between Music and the Structure of Universe, took us all on a deep dive into the connection between music and physics. And now he's done it again by bringing us a tour de force in what it means to think beyond the boundaries of sometimes rigid academic universes. Let me again welcome everyone to this talk and express my excitement in being here with you today to join one of physics' most original thinkers and someone I'm profoundly grateful to call my friend, Professor Stephon Alexander.
Thank you, Provost Peters. What can I say? I am dumbfounded. You know, every now and then I like to take opportunity to actually embarrass powerful people. And let me say that, you know, some of the things that I talk about in my book, Provost Peters actually lives that. I mean, and I really mean that because I met him, I think it was something like 25 years ago when I was an undergraduate. I was at a conference and there were a bunch of fancy physicists, like, you know, of an older generation. And I remember walking around, not feeling like I belonged. And there was the high table with all the big shot physicists. And one of the members of that group said, "Young man, come join us, come sit with us." And that turned out to be Professor Peters. And that was many years ago. And another quality that I talk about in my book is the importance to not be afraid of others, or not to actually embrace others that actually are bringing something new to the table. And he has always functioned that way throughout all the years that I've known him. So I guess what I'm really trying to say here is that I'll admit I'm a bit jealous. I wish he was my provost. So you guys at Abu Dhabi and at the Institute, it's a great pleasure to be a part of the NYU Abu Dhabi Institute, the first talk. And thanks for having me. I want to thank the staff and everyone involved in making this a possibility. And I want to thank the audience for attending. So without further ado, let's begin. I'm now going to share a screen and pull up, hopefully, the correct talk. So just bear with me for 1 second while I pull this up. Hold on a second. Why is it doing this? Okay, it should come on right now. And I just want to get confirmation from that you're seeing the full screen here.
Yes, we are. Yes, we are.
Very good. I'm just very good. So now let me play it again. All right. So this is the title of my talk. And much of what I'm going to talk about today is based on this book that I recently wrote called Fear of a Black Universe. And let's just begin. Well, you know, the story kind of really begins that during my graduate school years, when I was pursuing my PhD, and oftentimes, and all throughout my career, I actually realized that that Provost Peters used to do a similar thing. He used to go back to his homeland of Belize. And I would go back to Trinidad, which is where I was born, and moved to New York City when I was a youngster. But there was a special place in the northern coast of Trinidad called Las Cuevas Bay. And there's a chapter, the first chapter is called in the book, Escape from the Jungle of No Imagination. But really what it was about was every so often when I would get stuck on something, a problem, even of a personal type, or in my physics or in my career, I would go and trek up this hill and just sit and watch, just watch this bay. 7 miles away, you can actually, on a clear day, you can see South America, because Trinidad is 7 miles away from the Orinoco Basin, the mouth of the Amazon. And I would just wait for something from some new insight to come. And there was one particular time I remember it was when my grandmother had passed away and I was very close to her. And I had to reflect on my own life. What am I doing? What am I doing in my life? Why am I doing what I'm doing? Why am I pursuing the path of being a physicist when it's so challenging? It's difficult to make headways in the research. And then I'm receiving, you know, I'm a bit different. I'm a bit different in the way I think, the way I talk, the way I look, the way I walk, all these things. Why am I doing this? And I then had an epiphany. And the epiphany was, you know, go hard or go home. We have a saying, go hard or go home. But precisely what it meant was that I realized that maybe I was going about it the wrong way, that instead of just trying to get by, if I'm going to do physics, I'm going to do it. I'm going to pursue the questions that got me into physics to begin with. You know, why do we exist? Where does this world come from? You know, why, what is consciousness? How does that relate to the laws of physics? What is, how does, from non-living matter, living matter emerge? And what does physics, as a physicist, have to do with this? You know, I realized that I got attracted to physics because of the magical ideas, the magic in the obvious, the magic in, you look at the laws of quantum physics, and we'll talk a little bit about it today. But like, I was interested in the magic, and I wanted to create some of that magic myself, and not simply doing rote calculations on a blackboard or solving problem sets, right? And what I discovered was that after doing my own research was actually some of the founders of the field, like Albert Einstein and Schrodinger, and to name a few, were also risk takers. They didn't, so Einstein, wasn't a slave to the mathematics, for example. Mathematics was a very important tool, but the way he accessed his physics was through the idea of trying to devise principles first, trying to get some grand idea that underlies what appears to be, phenomena that may even be disparate, but he would find some unifying idea, right? And this idea would be encoded in something he called a principle. And there's a quote from him when he was asked, how did you come up with your theory of relativity? And he said, the theorist's method involves his using as his foundation general principles from which he can deduce conclusions. So today, what we're going to do is, I decided to approach my physics in the spirit and in the tradition of Albert Einstein and the other founders of the field, who also, again, were trying to look more at the general principles and then, of course, refine them, of course, with mathematics and theory. They were both necessary. So the other thing I want to kind of talk about now that kind of gives an overarching attitude, and this is when we talk about the title of my book, some of you may ask, why the title Black Universe? What do you mean by the word Black? Well, I mean, it can mean a lot of different things, but one of the things that I want to kind of couch this talk in is the notion of Blackness as a state of deviance, of a state of stigma. Now, oftentimes, when we think about what the word Blackness may mean in certain cultures or in language, it can mean that which is dark or invisible, unseen, misunderstood. They're all mysterious, right? Maybe there's a notion of fear. People fear the dark. So when we think about all that stuff, it's if we now think about groups of individuals or individuals, that you can now think about stigma, about having a dark thought, a thought that may get you an idea that can get you kicked out of the club, right? And now the question is, how do you navigate this stigma? And so when I talk about Blackness, I'm actually talking about in the context of physics, in the context of pushing the needle, taking physics to the next level. Sometimes one has to engage in some, what I call positive deviance. Sometimes an idea might have other people thinking, this person doesn't know what they're talking about. This physicist does not understand physics even to even claim what they're claiming. Now, this notion of deviance sometimes has a negative connotation in sociology, for example. The notion of deviance is that you might have a social group with the notion of social norms that the group agrees on. And if you step outside of those norms, you are now a deviance, and then you'll be subject to being shunned or punishment. And so, for example, breaking some laws is a form of deviance. Now, the kind of deviance I'm talking about is actually what I call positive deviance or active deviance. It's a deviance that actually, yes, may appear to break the rules or violate norms, in this case, the norms of the accepted physical theories at the time or laws or even mathematical techniques. But it's necessary to do that, right? To step outside and break those norms, because when, it provides an opportunity with good debate and with inclusive debate, right, to basically push the theory, the boundaries of those norms into new theoretical terrain, new breakthroughs, hopefully. Okay, so that's what I'm saying here is nothing too, I think Thomas Kuhn, the philosopher, said a similar things when he talked about paradigm shifts. But what I'm kind of doing here is to kind of bring this into the context of when we think about the issues of diversity, when we think about having people from other groups, from different cultural groups who are now engaged in the scientific enterprise, what they sometimes might bring with them is a different way of looking at things. And what I'm saying is that that is not in opposition. So sometimes, when we hear this when we talk about diversity, sometimes some people misconstrue that with somehow we have to, what's the word? The cat has got my tongue here. But the point is that there's some kind of compromise. I have to compromise what we know and what is already accepted to bring others in and bring other thinking. What I'm saying is that you need both. We should, there should be a striving to also excel and master the given techniques and norms, as well as embrace new thinking. It takes both to engage in new science and new physics. And so my book was really about not learning physics, because there are lots of books out there that's going to teach you physics, but this book is really about, a manifesto of how to do physics. Okay, so now let's get into some details. So again, the key method that Albert Einstein engaged in terms of trying to figure out a new principle was the idea of the thought experiment, or what you call a Gedanken experiment. And today I'm gonna put some primacy to 3 principles. So in the book, what I did was I said, okay, what are if I were to claim that there are 3 principles that can underlie all of modern physics, or most of modern physics, let me not to be too ambitious here, what would those be? And and the idea is, if I were to kind of combine these 3 principles, maybe I can generate some and say new things, new bold things or not about physics today. And I'm going to list these principles and talk a little bit about all 3 of them. And the first principle I'm going to talk about is invariance. And this principle, so what I'm doing here is that all these principles actually have been stated in the past, okay? But what I'm doing is I'm saying, what I'm claiming here is these 3 principles are to be placed as fundamental when we think about the operation of our physical universe. So let's begin. The first is, and one last thing. Obviously, I am a musician, and one of the things that we do in music, of course, is that we take rhythm and harmony and melody, and it's when they get combined, we get something that starts looking like music. So I want us to think of invariance, superposition, and emergence, for example, as these different components. And I'm going to compose the ideas, I'm going to combine them, of course, to compose a new physics. So that's kind of where the improvisation is going to happen. And of course, the 4th principle, I said a little bit, positive deviance is what I call the principle of blackness. So the first principle I want to talk about is the principle of invariance. And basically, if a friend asks you, this word is such a big fancy word, what is the what is the heart of the matter here? What is invariance? You can say the invariance principle, as my good friend Casey Cole, writer, said, it's the change that doesn't make a difference. So, you know, when we sometimes we think about what change in something is, means that you literally change usually means difference. It means that if I change my orientation, I change my position, if I change my hairstyle, right, it looks different. But at the heart of invariance, it's the idea that if I basically have a physical system, for example, and I rotate it, there are certain aspects of that system that will remain unchanged. And the question is, what are those things? All right. And it turns out what those things are, these things are, for example, quantities that are what we call conserved. So for example, you want to wonder why when the Earth is spinning around its axis, why it will just continue spinning is because of a rotational symmetry having to do with basically the fact that the Earth is nearly almost, you know, spherically and rotationally symmetric. And therefore, if it's set in motion in a rotation, that angular momentum, its rotational motion, will be conserved, will not change in time. It will continue spinning about its axis. So there are tons of, not tons, a handful of invariances, or another word for that is symmetry, right? The link between what remains the same about a physical system and basically its symmetry, okay? The fact that if I rotate the Earth, if I take a perfectly symmetric sphere and I rotate it, it looks the same as the unrotated sphere. So the physical laws are codified by symmetry or invariance. So let's give some modern examples of this. So what we're looking at here, I mean, here, and this is something like I would literally teach in my, actually a couple of weeks ago in my quantum field theory class. So what you see to the left is a X, Y, and Z axis. It's used to sort of specify the position of some observer. It could be you sitting at the center of that coordinate system. It could be an airplane moving. And the blue.
Dr. Stephon,
Yes.
Stephon, I'm sorry to interrupt you, but we only see the first slide. We're not seeing your other slides.
Oh, this is not good. Okay.
We only see Fear of Black Universe, the first slide of your presentation.
Well, thank you for telling me that, because
absolutely, okay. Of course. Okay, great, yeah. Well, try again to share your screen.
Yeah, so what I'm gonna have to do is to not make this thing,
yeah,
I'm just gonna have to do it this way, and yeah, for some reason.
Okay, okay.
All right.
Thank you very much.
So I wanted to show you the picture of Las Cuevas Bay. That was my first slide. I wanted to show you this, the idea of Einstein's principle theory when I talked about his method, basically to use principles to understand physical law. And I basically wanted, when I talked about positive deviance, what I want to really highlight there is that what we're doing is not learning physics here. It's about doing, the act of doing and creating new things, creating new physics. And positive deviance is basically embracing the outsiderness, outside thinking, if you want to say, away from the norms of a paradigm. And my point was that it's not an either or, we need both. We need both mastery and the striving to understand and master the known techniques and the norms, as well as embracing outsider thinking. And right, so that's the idea of positive deviance. And what I was talking about here are these three principles: invariance, superposition, and emergence. So what I want to talk about now is the invariance principle. And this very important slide kind of gives you the essence of Einstein's theory of special relativity. The fact that how Einstein discovered this was to actually use this idea of invariance. And I want to kind of talk about this very magical form of invariance. The question is, to talk about invariance, I got to talk about what changes, right? So what changes here is that we have somebody that's staying put and somebody that's moving along. So what's changing is the fact that you have two individuals, and this diagram is supposed to represent a coordinate system moving away from another coordinate system. And the question here is, obviously, what changes is that if you're watching something, right, and that thing is fixed. Say you're watching a train at rest. the train stops, it's at rest, but somebody is moving along and they're also watching the train, they will perceive the train to be moving, but you are perceiving the train to be at rest. So the question is, clearly there was a change there. And what Einstein realized was actually there is a secret operating in nature, that there were some things that actually didn't change, even when you have observers that are moving with respect to each other. And what he realized that did not change was the speed of light. Okay, so you can say, well, that's really weird. How is it that the speed of light can't change? Well, the trick was, and here was the underlying trick. You're moving through space, right? So you know, we are thinking that, hey, we are in a reality where we have three-dimensional space and then time is flowing along. So Einstein's hack was to realize that actually, if you were moving not in a three-dimensional space, but a four-dimensional space-time, that situation, right, is not changing actually for both observers. All right, and the picture to the right is supposed to gives you basically what a little bit of like what that geometry looks like. It looks like basically a cone, and we call this thing a light cone. Now, I'm just giving you this talk a little flavor. It's an invitation for you to go and read the entire chapter, where I kind of go into, you know, whatever, 40 pages of pedagogy. But the point of not pedagogy, but trying to clearly understand this idea. One way to think about this is if I'm at the surface of a sphere, right? And I move from one point of the sphere to the other, even though I may appear to move to a different position, there is something that doesn't change. And what doesn't change is the radius, the length that connects the origin of the sphere to the surface. When I rotate around, that length does not change. So what Einstein realized was that that length is like the speed of light in a four-dimensional space-time. So basically, at the end of the day, the thing that didn't change is the nature of this four-dimensional space-time reality that we're all living in. And we are just nothing more than projections of that, thinking that we live in three dimensions. So again, he was able to eke out this reality that we can't directly perceive about four dimensions by undergoing these thought experiments, asking questions about when things move, what does not change in this? And he realized the speed of light doesn't change. That came about from another thought experiment that he had. But again, this is an example. I'm going to give you another thought experiment. And this one was Einstein's happiest thought. Again, this was underlying his theory of general relativity. And it uses some of the most beautiful mathematics. And actually, Provost Peters is one of the world's experts on this type of mathematics called differential geometry, where he applied it to basically advances in gravitational lensing, something I'll talk about later on. So basically, what Einstein realized was another symmetry. Here's a symmetry. The symmetry is the symmetry or the invariance. The thing that doesn't stay the same is the following. Let's actually look at this thought experiment. Somebody is in a, some kind of, contained in a wall, not in a room, a very small room. They cannot see what's outside. They can't hear anything. They have no information about what's going on outside. But what they could do is know something about gravity. So they can drop something and see it fall. So one morning they wake up in this room and they drop things and they're like, oh yeah, I'm clearly on a planet and I'm definitely fixed in some room like you are right now, right? We are all now in a situation where we're in some type of room and we're not moving. We're fixed to the earth. So this person concludes that. There's another person though, who is in outer space where there's no gravity and they're being accelerated upward. And they also drop a ball and they experience the same thing. What Einstein realized that these two situations are equivalent. They're the same. They cannot, you get the same physical outcome in a situation where you're not moving at all, right? In the presence of an Earth's gravitational field, and where you're moving in outer space where there's no gravity. And so he basically claimed that there is an invariance. There's a symmetry between moving or accelerating and not accelerating. And that was the key to him then realizing that there's a principle here at work. And this principle has to do with, you have to basically give up any description of a fundamental coordinate system, that even the notion of labeling a coordinate system is actually a fiction. And he was able to go beyond that and devise his theory of curved space-time, that the underlying reality, the thing that's hidden from us, is actually that space can warp. Okay, also time could warp as well, but that's another question. So these are two great examples of where Albert Einstein was able to use invariance as a diagnostic to discover new laws. And of course, the mathematics came along with that to help us refine and make more precise statements. And so I now want to move on to another principle. Oh, by the way, can I ask how much more time I have available to me?
You have another maybe 20 minutes.
All right, so I have to move quickly now.
Yeah.
The second principle I want to talk about is the superposition principle. This is the principle underlying quantum mechanics. And the way I want to talk about that is to talk about music. You see, every musical note, you can think of every musical note as the realization of a vibrating wave. So you see to the top here, when I look at basically an air wave inside of a flute or a wind instrument, that wave is basically undulating. And the ones that are below are undulating or vibrating at a much faster rate. And the different rates at which those waves are vibrating gives me the different notes and the different tones. Now, there's a particular mathematical relation, which are the sort of, at least in Western scales, the notes of what we call of our major scale are all related to each other by integer relations, meaning that as you see there, the wave is divided into integers, right? 1/2, 1/3, 1/4, 1/5 of the original waves. So my way into this is to think about that waves, they're very special waves, and that the waves basically come in these different varieties. But I can do something else. I can superpose these waves. So for example, if I play three notes at the same time, that's like adding these three waves together to create what we call a chord. And in mathematics and physics, this idea is called superposition, and it's behind a very powerful idea in engineering and physics that has a fancy name called a Fourier transform, which is that if I add these three simple waves, these three notes, I get a more complicated looking resultant note, right? And that's the essence of superposition. Quantum mechanics uses, at the heart of quantum mechanics, this is the underlying principle that makes the quantum world dramatically and majestically different than the world of the macroscopic. So what is weird about this? Well, I told you that every note is like one of these waves and they can be added up together. But imagine if I told you that every wave in the quantum world actually corresponds to the position of a quantum particle. So imagine I tell you that if I consider one and only one quantum particle, that basically I can superpose or add many different positions of that one particle at the same time. Now you're going to say that is totally voodoo, right? Because when you look at things in the real world, right, things have a unique identity in terms of its position, in space. In the quantum world, what I'm saying is that at the heart of the quantum world is this superposition principle, which tells me that actually I have no choice, actually, but to actually consider multiple positions or velocities or different qualities of the same quantum object. And that should be weird. And no quantum mechanical expert I know personally is yet comfortable with this idea, but it is at the heart of actually all of the properties that we use in quantum mechanics. We are now thinking, of course, we're building quantum computers. This property of superposition is actually at the heart of the devices behind the quantum computer. So it's a very real thing. This is not, while it seems to be weird, it is actually not sci-fi. But obviously people have made sci-fi movies based on this idea. So again, our way into this is to look at basically how an instrument works. One of the triumphs of understanding atoms in the quantum world was that the orbits of atoms in the early days of classical physics was unstable. That physics allowed basically the electron to fall into the nucleus. And it was the French Prince violinist, Louis de Broglie, who basically took the idea of a vibrating violin or string instrument to realize that the notes on a vibrating string support these waves that I was talking about. And he realized that you can wrap these waves around, as you see there. And if you identify the orbit of the electron as actually a wave, then that would solve the problem. And not only did it solve the problem and stabilize the orbits because there's the lowest note will just correspond to the lowest frequency. And if you identify the orbit of the electron as the lowest frequency, well, it cannot never fall in because it's using this wave-like property. So anyway, to make a long story short, Louis de Broglie was able to then apply this idea. And then later on, it was Schrodinger and his contemporaries that developed the full mathematical theory of quantum mechanics. And now what you're looking at here is basically the vibrational patterns of the electron's orbit in hydrogen. These are, mathematical and of course experimental realizations that basically, when you think of molecules and the bonds, they are not particle phenomenon, but they are resonant vibrational patterns, sort of like vibrating sand on this vibrating plate. Notice that if I tune the frequency, this random pattern of sand on this surface will start forming one of these vibrational patterns. Okay, so this type of physics is what's going on in deep down in the quantum world. And again, this superposition principle leads to some very weird consequences. Like I can be in a superposition of a dead cat and an alive cat if there's a quantum event that triggers its, the poison coming and killing the cat or not. And there's this idea now, if I watch something versus not watching it, do I disturb the superposition? And so there are lots of philosophical questions there. And of course, it's, I hope, covered nicely in my book. So I'm going to skip this in the interest of time. Here is something that I think is quite remarkable. These are what we call Feynman diagrams. And what you're looking at here are superpositions. Each diagram corresponds to some elementary subatomic particle event. And this is basically these diagrams, and this is another interesting theme of my talk, which is different perspective of seeing the same type of physics. So in this case, Richard Feynman was able to turn his mathematical equations into an equal representation of art. So instead of doing these really complicated calculations that would slow him down or muddy up a clear idea of what's going on in the physics, Feynman devised these diagrams, these beautiful diagrams that encode all of the mathematics. And so what we're looking at here are superpositions of elementary processes of the same entities. And what you find is that if you add these up and you then calculate a number, that number will maybe correspond to a tiny little magnetic, magnetic field of a particle called a muon. It's a heavier cousin of the electron. It turns out you'll get 11 decimal points of accuracy, meaning you'll get a 0 with 11 decimal points that you could go compare to experiments. So what I'm saying here is that the superposition principle, while it's weird, it's actually seems to be functioning in the subatomic world. I'm gonna skip this here because as a musician, I've also been a little bit deviant and worked with jazz musicians to apply some of these quantum ideas into jazz improvisation. And in my first book called The Jazz of Physics, I kind of talk about this quantum improvisation. One day when I come out to Abu Dhabi, I'm more than happy to play some of that. So, and here's a picture of a Feynman path integral not with atoms, but with notes. So I'll let you stew over that a little bit until I see you in person. Now, the last principle I want to talk about is the principle of emergence. Now, principle of emergence is, in a sense, how do you think about it? Think about it in opposition to what we call reductionism. A big part of 20th century physics was basically going deeper and deeper into smaller and smaller distance scales and discovering more and more, the idea of atomism, more and more fundamental elementary particles. And what we discovered was the deeper and deeper we got to look shorter and shorter distance scales to find these more elementary particles, that these particles and their interactions, the way the rules that govern their interactions enjoyed more and more symmetries. So we thought, hey, let's just keep going there. And something like superstring theory is you probably heard about this idea. Superstring theory is an idea that's very beautiful, and I've worked on string theory. I still think it's a beautiful idea and worth pursuing. I'm certainly doing that, as well. But that idea basically lends itself to the idea of reductionism. Emergence, you can think of it as the opposite. So what we're looking at here are, imagine that I have my elementary particles, and I've reduced reality down to saying, the laws of nature is all about that. That's it. And then I can build up everything. I can understand atoms and life and viruses and all that stuff. Emergence says not quite. What emergence says is that while you do need these elementary particles and their interactions, the interactions themselves and the particles and the properties that say smaller subsystem has cannot fully explain certain properties that emerge, for lack of a better word. And I want to give you some example of, so the principle of emergence, I just want to state it here, is that systems with interaction elementary parts, for example, atoms, atoms corresponding to gas. And at some point, if I cool it enough, it becomes a liquid, but it's made up of the same atoms and the same interactions. Now they have different properties that cannot be explained or reduced to the basic interactions. So systems with interacting elementary parts can exhibit novel properties that are not possessed by those individual constituents. So we have this little picture here that tries to get to this, which is that you have these individual interactions, but then you have an emergent structure. And here's one example of ants that individually don't know anything about a bridge, but they create an emergent phenomenon that has a new functionality. And that functionality is basically to build a bridge so that the other ants could cross over. The individual ants cannot do that, nor can 3 ants do it. You need this emergence. You need a collective behavior of the ants to give this new emergent property. What is the emergent property? The functionality of a bridge. So some other examples of emergence is people with our own individual psychology and languages, but we come together to create an emergent property called culture. We have atoms. Atoms are not living, so most of us think, but when atoms come together, they make a cell, they make living things, and that's the emergent property that's not contained in the individual atoms. Neurons, some people believe that consciousness is an emergent property, or complex human consciousness is an emergent property of how neurons are wired together. So there are lots of examples, but my point here is to make emergence fundamental, make it a fundamental principle of nature. Not something that is only relying on the constituents. It is basically encoded in our universe. That's my point. So some of the things I play with in my book is maybe some wild ideas. So the rest of my talk is to kind of talk about some of these wild ideas. So one wild idea is, well, how could maybe space and time itself can be emergent. What does that mean? Because that's a weird one. What does it mean? It's safe to say that in many of our experiences and perception and imagination of space and time is that it's something that is a priori empty and in front of us. It's this stage that we can move in. Well, obviously Albert Einstein toppled that idea and showed that space and time is a dynamic, malleable entity, and why it still, presides to be invisible. That's for another discussion, is because space and time itself is a field, right? Like the same way you can have a magnetic field operating between two magnets. You can't see the magnetic field, but you can feel the forces. So there's something, though invisible, happening that's basically making these magnets speak to each other between the empty space. So, but what about the idea of no space then? And so can we think of some, lack of a better word, atoms of space-time, where you have a pre-geometry, a pre-space-time? What does that look like? Well, how do you conceptualize that? So in the book, I talk about that there could be atoms of space-time. The notion that space-time is really an operational thing. It's something that it only exists in relation to a thing that is in the space-time. And there's a notion of fuzziness one's location could actually be fuzzy with respect to, the energy one puts into observing the space-time. So there's this interesting interplay that can make even space, the notion of having pre-space before having this smooth, continuous property of space-time. And that idea is not done. It's still being pursued by others. There are different variants of it. And in the book, I kind of give my own variant of it and talk about actually that space contains in it atoms of consciousness. And that's what's weird about this, okay? So what do we mean by atoms of consciousness? And what I do in this is actually, I draw from African philosophy, actually, from the Bantu Congo philosophy of something called Ogbunu. So, actually, I'm not remembering the word precisely, but it's in my book. So that's a nice little teaser. It's at the end, the last two chapters of the book. And this is now a little surprise treat for Arlie. So she spent a lot of time thinking about dark matter. And what is dark matter? So I'm going to finish my talk off now by talking about this other wild idea. Remember, I told you that the quantum principle, if it's fundamental, then therefore it should not only, we only think that the quantum mechanics is operating at subatomic scales. But what do I mean to make a principle fundamental? It means that it should operate everywhere, including in regimes or in situations where we should not expect it to operate. So here's a crazy or wild or black idea. So what we're looking at is a rotating galaxy. So a galaxy comprises of a disk-like system of stars that are rotating around a common center, like a frisbee that's rotating. Now, it has our Milky Way galaxy is what we call a spiral galaxy. It comprises of on the order of 500 billion stars like our own sun. And it's all going around at some velocity. So Newton's laws tell us that you can weigh what's in a rotating system by how fast it's going. This is called Kepler's law. So what we're seeing here is what we expect of this physics of Newton and what Einstein and Newton taught us, which is that when I go further out, the galaxy should be rotating slower at that position, given the amount of mass that we observe. And what we see instead is this white curve, that it's not slowing down. And so what that means is that we need some form of matter to compensate for the rotation that we actually see. And in fact, how much of it is needed? Well, 85% of it is invisible and missing. We call that invisible matter, dark matter, okay? So it's the invisible amount of matter that's needed to make our galaxies rotate. Now you can say, well, why do I care about that? Well, remember, our sun is kind of at the outer edge of our galaxy. And if dark matter did not exist, our sun will be in an unstable orbit. So we'd be in trouble. We'd go flinging off. We'll be in an unstable orbit. So because of dark matter, we're able to sustain ourselves going around our galaxy in a stable orbit. So this is cutting edge research. We don't know what the dark matter, we know it exists. We just don't know its character, what it's made up of, why it's happening, why does the universe need it? You know, how could something invisible weigh so much? I mean, so there's all these questions. And I want to play this little video showing this idea of a quantum fluid. This is something that happens, an emergent property, but it's a quantum emergent property. So what we're doing is combining the quantum principle with an emergent property, which is that I have a gas of hydrogen gas, and what happens is a collective emergent property where it becomes what we call a superfluid. So I'm gonna play this, and I believe that this is courtesy of the BBC. So I want to give credit for that.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particular is happening. Well, this is really one of the great phenomena in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed
So let's see what let's see.
ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
All right, so that should be weird. The reason why is that the superfluid is what's super here is it's a quantum fluid. And ordinary fluids, if you contain it in a glass, like my coffee here, it's gonna stay there. Well, what a superfluid does, it creeps over. It has negative pressure. It's able to escape and creep over. And that's because it's actually what it's doing is undergoing a phenomenon called quantum tunneling. So it uses these weird quantum properties. And the new idea is that the dark matter actually is an emergent quantum property that is not acting on only microscopic scale, but on galactic scale. And the idea is that our galaxy is a what I call in the book, a quantum galaxy. The galaxy is a superfluid. And you know, we can learn about this. So one of the things that I always like to, you know, I see that Ollie is smiling. He's seeing a picture of a gravitational lens, which is this idea that we can know about dark matter, even though it's invisible, because if it's heavy and contained in a galaxy, according to Einstein's theory, it could warp or lens the space around it. And so if I look at an object behind it, the same way I look at an image behind a magnifying glass, a lens, it will distort it and make it look different than what it actually is. And what we're looking at here is a real picture from the Hubble Space Telescope, where we see a ring. That ring is a lensed image of a warping of space-time due to the effect of dark matter in a galaxy. And that what you're really seeing is a sequence of the same galaxy that's lensed around like a kaleidoscope. It's a real picture, a real effect. And we can use gravitational lensing to now look for properties of a superfluid galaxy. And what is one of those properties? You're going to have an emergent phenomenon. You're seeing these whirls. Those are things like a sandstorm or a hurricane. We call these things vortices. And superfluid, quantum superfluids actually predict this phenomenon. So we are now, I want to kind of end by saying that sometimes venturing out into these uncharted territories that you're told you're not supposed to do, by engaging in this positive deviance and by using the principal ideas that I was talking about, sometimes you could construct new theories. And I want to kind of end by saying that this is one of those new theories that I and my colleagues were able to get at by engaging in the principle of Blackness. So thank you for your time, and it's been a real pleasure. And I look forward to seeing you all in person very soon in the near future. And again, thanks a lot.
Thank you very much. Thank you very much, Dr. Stephon. Dr. Arlie, would you wish to open up the Q&A session? The questions are under the Q&A, so if you want, you can pick up a couple of questions and direct. Otherwise, I can do it. I'll be happy to do it.
Okay, yes. Well, we can surely share, Nadia. Well, thank you for such an excellent presentation. I'm extremely inspired. And I will say your talk itself created an emergent phenomenon because my mind was just going. So thank you for that resonance. So we have some questions in the chat, and Professor Nadia Sheikh, also Vice Provost, she and I are going to share the questions. So this one deals with, I'll begin with the first one, Nadia. Is I'd say relates to career matters. It's how is it possible to be a good physicist in an H-index dominated era? So I guess the academic analytics may be, does that really interfere with this creativity you're talking about, right?
Yes. It's a very
going outside the box.
Yes. Well, you know, so full disclosure, my whole thing is that, well, you know, there is a thing as H index, but there's also what the H index is doing is it's supposed to be some form of a metric or some type of measure of impact. But certainly I know of great physicists with a relatively low H index, but their impact is tremendous. So again, I would think more in terms of impact as a fundamental principle, and the H index as some, you know, some measure, but albeit limited. And I think more importantly is the question of impact, and that's why I'm happy that you have a provost like Arlie Peters, who is going to change the rules, you know, and grant tenure based more on impact. I could turn the question more on. I think that's more of a question for you.
Well, you know, I think that indeed you hit on a very important point in that creativity comes in so many different forms. And there are times when assessing that, we should not become too much dogmatic about certain kinds of academic analytics. Some of the most creative people had very poor grades, right? They didn't perform well on standardized tests. They may not publish a lot. So these are the important things you're pointing out. Nadia, did you want to take the next one? I think you're on mute. Yeah.
Yes, so someone is saying here, I'm probably way off here, but is a black hole's enormous gravity, which causes the bending of time, a macro example of quantum mechanics?
That's a fantastic question. And I think the way to really get at that is that if we had a quantum theory of, so we know from Feynman's way of thinking about quantum mechanics that the classical world emerges from that quantum thing. And so what we'd love to get is a quantum theory of gravity that may describe a black hole, and see whether or not that's a very good question. It's actually a good research question. I don't know the answer to that, but the question is pointing basically to a need for whether or not we do need a theory of quantum gravity or not. Is it sufficient for the black hole to just be described by its event horizon, classically?
Right.
Maybe I'm sure. I would like to open this up to something that's kind of looking like a conversation between me and Provost Peters, because I actually like to hear his thoughts about that too. I know you've thought a lot about black holes.
Yes. So, well, you know, we have a lot of fascinating questions in this regard. And so I'm going to pick a different one. It says, thank you so much for the talk. I'm amazed by your thoughts about the interaction between physics and music. Could you talk more about your exploration of music?
Yes. Yeah, that's a great, thank you. I mean, one of the things, just like, you know, I like to say that a really good physicist is a very dumb person. I actually really mean that. You know, like I think that you and I, we see this the same way. Actually, we're always striving to find the simplest or dumbest or most basic explanation for something that may appear to be very complicated and bewildering. So we're always trying to strip it down to the simplest thing. So the way I approach my music and my jazz improvisation is that, there are all these notes and chords and scales. I'm trying to basically strip it down and see, is there something underlying that if I understand that, then it enables me to just really get a better hold of the improvisations I'm playing. So yeah, sometimes I do analyze my music through the lens of symmetry, or what are the basic, there are thousands of chords, but are there maybe 2 or 3? But if I know those 2 or 3, the others just can emerge. So yes, that's exactly some of the things I engage in. And in fact, engaging with some colleagues at NYU, Abu Dhabi, and in New York City, Robert Rowe and his colleagues, actually in some of this. So, NYU Abu Dhabi is actually unique in the sense, had a conference, I think, not too long ago, that talked about the geometry of musical rhythm. So looking forward to continuing on that exploration, actually.
Mm-hmm.
Another question on black holes is about how are black holes related to dark matter?
That's a very good question. We expect some sort of relation. It's something that I know I've been thinking about. I know other people have been thinking about. I believe some years ago, even Provost Peters looked at higher dimensional black holes. And, there's some ideas that connect in a high dimensional framework, the relationship between black holes and dark matter that could be looked at again, actually. So thanks for that question. So the answer is, we expect some correlation between them, or some causation or interconnection between the two things. They're operating on very different length scales. I mean, you're talking about something on the order of 10,000, 10,000 parsecs versus something that's contained, a few solar, the size of a solar system. So, but yeah, so we expect some connection. We don't know the answer.
Okay. So the next question is space-time like a field, 2-dimensional, or is it covering everything inside it, such as us, like chocolate chips in a muffin?
Mm-hmm. Well, that's right. So space-time is a weird type of field because it's a field that defines a space. It occupies itself. So, right. So in other words, one way to think about this is that if I hold a magnet and it has a magnetic field, that magnetic field is occupying space-time. But the space-time provides the space itself for it to occupy itself. So it's a weird, even more weird, bizarre concept. It defines its own background. Okay. Right.
Professor Alexander, can gravity be explained as an emergent property?
So there are physicists right now as we speak that are trying to do this. I believe that all those models are at this stage of the game. Toy models, what we call toy models, which are, again, very stripped down, unrealistic things where we can play with the equations to get some insight. We're not there yet, but do I think that, that gravity, space-time is an emergent phenomenon? I think it is, but it's the weirdest one. If it's gonna be an emergent phenomenon, it cannot be like the other ones. It has to be completely bizarre. And that's why I think that it has to involve consciousness. Now, let me use the word proto-consciousness. Do not project our human kind of consciousness on this, all right? And so I kind of speculate about that at the end of the book, that there's an emergence due to the activity of a proto-consciousness. And I'll leave that for the end of the book.
That is a really nice way to say go out and buy the book. This is fantastic. So this one, Stephon, picks up on, of course, the important diversity issues that you raise.
Mm-hmm.
Have you had any collaborations with researchers at African universities If so, I'd be curious to hear the topic's findings.
Yeah, so, I'm very, so I consider, I'm sort of like, what do you call it? There's a word for this, a person that I'm a diasporatic thinker. I mean that I look at the diaspora, including Africa, as one whole continuum. And so I don't really see much of a difference between, collaborating with, though I've written papers with Manasseh Mbonye, who is a Rwandan cosmologist and a good friend. And we, in fact, some of the origins of this quantum galaxy idea came out of that early collaboration. And then, but, I'm very proud to say that it wasn't anything that I was deliberately doing, but I've happened to, have written like, 6 or 7 papers with Black physicists, I'm very proud of that. Ollie and I, we were working on something, and he became a provost. But maybe he could sneak a thing or two in the future when he's less busy. But my point is that does something different come out? Is that if that's what the question is pointing to? And I think that if that every collaboration does have a difference in who, and that's the point. The point is that when you collaborate with people with different cultural lenses, even though you're talking the same mathematical language, it's going to paint, right? It's going to color, for lack of a better word, what comes out. It's going to color the engagement. It's going to color the style. You talk about style. I mean, when I was in England, the English physicists, the way they were talking, the way that the Blackboard were kind of different than the Russian physicists, were kind of different than the French physicists. And I think the same happens, when other cultures are engaging as well. It's not to say that that is the main difference, but I'm saying that it's a beautiful thing, and we should do more of it.
The speed of light is constant, but time can warp. Please give your view.
Speed of light is constant, but time can warp. Well, that's okay. Time is not time. Okay, speed is a composite of time and space. To talk about speed, you need to talk about how far an object, is displaced in a given unit of time, right? Whereas time itself, right, is not a composite. It's literally a dimension, right? It's one of the legs in the 4-dimensional space-time continuum. And it's interrelated with the spatial dimensions in the sense that there's a symmetry that can swap space and time that says, you know what, the one thing that happens when I swap space and time is that the speed of light still remains the same.
Provost Peters, this is the last question for our speaker tonight.
Well, I think the ideal way to end tonight is a comment from one of the viewers. Thank you for enlightening us tonight. This was an emergent moment.
Thank you as well.
Thank you very much, Professor Alexander, for this incredible talk. We hope to host you in person sometime soon in Abu Dhabi. Thank you, Provost Peters, for your recommendation and for joining us tonight and for helping us communicate with the Professor Alexander. Stay tuned for those who are attending the talk. Please stay tuned for our programming, and hope to see you on campus sooner than later. Thank you very much.
And thanks again for a fantastic talk, Stephon. Y'all take care.
Take care.
Bye-bye.